So I'm going to have a statistics digression. If you do Statistics 101, they tell you you shouldn't have more parameters in your model than you have data points. You really ought to have quite a few data points for each parameter. It turns out this is completely wrong. Bayesians knew it was wrong, actually. The brain is not in the same regime as Statistics 101. In the brain, you're fitting about 10 to the 14 parameters, and you have about 10 to the 9 seconds. So even if you have sort of 10 experiences per second, so even if you take 100 milliseconds as the time for an experience, that's the kind of backward masking time, you have like 10,000 synapses per 100 milliseconds of your life. You're throwing a lot of parameters. So if your mother just kept saying good, bad, good, bad, good, bad, she couldn't possibly provide enough information to learn all those 10 to the 14 parameters. And here's what they teach you wrong in statistics. Everybody knows that if you've got a given size model with a given number of parameters, the more data you have, the better you'll generalize. So for a given size of model, it's always better to have more data. In fact, the best thing you can do is get more data. Okay. But that doesn't mean that if you've got a fixed amount of data, you should make it look like a lot by having a small model. That's what they tell you in Statistics 101. Okay? Big models are good if you regularize them, if you stop them doing crazy things. We can see that using a lot of parameters is good, that you can always win by having more parameters. And the way you do that is say, I'm going to have a committee. I'm going to learn lots of different little neural nets. You give me more parameters, I'll learn more different neural nets. And then I'll average what they all say. And you'll always win. It's a sort of declining win. But if you have enough of them, you'll win by having more. So it's always better to have more parameters. It turns out, if you have a fixed amount of data, and you have enough computation power, which the brain has, you should always use such a big model that the amount of data looks small. That's the regime you ought to be in for a fixed amount of data. That is, if you take the limit when the amount of data is fixed, and you have unlimited computation, and ask, now how big would you like your model to be? You'd like your model to be much bigger than the data. Okay. Now, that only works if you have a good regularizer. And I'm now going to tell you a very good regularizer called Dropout. So this is to use in neural networks where you have a lot more parameters than you have data points to train them on. And you could learn an ensemble of little models. And this is a way of learning an ensemble of many more models, but the models in the ensemble can share things with each other.
The question is that I was trained with this intuition that you can't over-parameterize your models, that if you're trying to fit a line that you need 2 points, if you're trying to fit a curve you need 3, and so on, and that scales up, and you should always have a little bit less data points. So I know that you have shown clearly, and the field has shown that that's not true. What were the statisticians getting wrong in their logic to be convinced?
It's to do with regularization, that you need it to be highly regularized. But first of all, I'll show you that if you want to fit fit 2 data points, well, let's take 3. If you want to fit 3 data points, you would have told me you want a polynomial with only 3 degrees of freedom. So you want a constant and a slope and a curvature. And that's all you can afford with 3 data points. Mm-hmm. That's wrong. Now, this is where we need a pen.
Oh, sorry.
They don't work. I tried them all, and none of them work.
Here you go, I got them.
Okay, do they work?
Well done. Extra points.
Okay. Yes. Can you see that?
Yeah.
Okay, and we're going to have 3 data points. And actually, if you're a statistician, you'd probably say for 3 data points, you probably ought to fit a straight line like this. Because I could fit a parabola, and the parabola would fit exactly, and that's a bit suspicious. In other words, the parabola fits exactly, but do you really believe that if you were to ask when x is 0, what's the value of y, do you really believe that value for y? Because a straight line is far more conservative, right? So a statistician would probably say fit a straight line. However, that would be a frequentist statistician. If you took a Bayesian statistician, and this is in Chris Bishop's machine learning textbook, there's a nice picture of it, I think, somewhere. I think it's that book. A Bayesian statistician would say, okay, let's try fitting fifth order polynomials. And fifth order polynomials, we might even fit ones that don't exactly go through the data, but for now let's make them go through the data. So we fit a fifth order polynomial that goes kind of 1, 2, 3, well, you know, some order. And we fit another one. Oh, that didn't go through the data, hang on. And we keep fitting these guys, and we fit a gazillion of them. And what you see at the end is that these gazillion ones, in between the data points, they're kind of all over the place. And their average is in a sensible place like here. But their variance is big. And what they're telling you is, if you give me this x coordinate, I'm rather uncertain about this y coordinate, but this is a good bet. And similarly here, and if you go out here, these polynomials are just all over the place. And they'll tell you, if you give me this x value, then it could be pretty much anything. That's not a bad bet, but it could be pretty much anything. And that's a much better answer than you get from a straight line.
Yeah.
So by fitting a very large number of different polynomials and then averaging, you get good mean answers, and you also get a sense of the variance.
Okay.
Now, dropout is doing something like that.